Good afternoon, everybody. Normally we start with a do now, but the structure of this week's class is a little bit different because we're trying to go over a chapter of material and do exam review. So what we're going to do is start with chapter 3. And I know you may not have had time to watch the video first, so I'm going to hit on some of the key points from chapter 3. We'll do a little bit of practice together. Then we'll vote on whether or not you want to take a break or just move on to the exam 1 review. In that kind of in-between time, that's when we'll talk about the upcoming exam, and I'll give you kind of the logistics. You can ask questions, and then we'll move forward. So with that said, we're going to get started with chapter 3. Chapter 3 starts with looking at solids, liquids, and gases, the 3 states of matter. Pretty sure that you have encountered solids, liquids, and gases somewhere in your schooling already. So we're not going to take too much time to explain exactly what a solid, liquid, or gas is in those, in the kind of definition type of way. But we are going to talk about the properties of solids, liquids, and gases. So I've listed 4 properties that you need to be familiar with. And then I've got a word bank below that I'm going to use to fill in the blanks for each of these states of matter. This will be our way of reviewing what solids, liquids, and gases are and giving you the terminology necessary for doing these types of problems. Multiple choice, fill in the blank, matching, that kind of thing. So I know several people have just joined. Just to catch you up, we're going to start right away with chapter 3 material. No do now. If you watch the video, you can chime in, you can help, you can fill in the table in your own notes. If you didn't, just kind of hang with me, make sure that things make sense. I'll clue you in on kind of the types of questions that you'll need to be able to answer with chapter 3 material. And then we'll do the exam review. All right. So first, solids, liquids, and gases. Let's talk about shape and volume. Think about a solid in your mind, So let's say you have a coin, right? The shape of that coin is fixed. It's not going to change if you put the coin into a cup, if you put the coin on the floor, if it's on the table. The shape of that coin is going to be the same. It's fixed. Same thing for the volume. No matter what you do to that coin, the volume is going to be the same. You're not going to change it. Solids are not significantly compressed. You can press on them. Maybe you'll compress it by like a fraction of a fraction of a fraction, but it's nothing that's going to be noticeable. So for compressibility, it's not significant. The last row is about energy. And this relates to the kinetic molecular theory. And simply stated, the farther apart the particles in a substance, the higher their kinetic energy. In a solid, all of the particles that make up that solid are very tightly packed in. They're moving, but they're not moving very much. They're just kind of vibrating in place. That means that solids, relatively speaking, have a low amount of energy. Let me know if you're with me so far. I know a lot of folks are still signing in or logging on. All of the information that I'm going over for Chapter 3 is in that lecture video. So this week you will definitely need to watch the lecture video because we are not going to hit all of the points in Chapter 3. If you just use this live lecture to, say, okay, I know Chapter 3, no, you don't. You absolutely do not. We don't have time to cover everything. And the exam one review is more important, I think, for you guys than me going over everything in Chapter 3. Raise your hand if you can hear me. It looks like... Okay. So it's not on my end. All right. Then whenever you see somebody type in the chat they can't hear anything, remind them to, 1, make sure their computer isn't muted, and 2, you might have to exit and then log back in. So we completed our column for solids. Now we've got to do liquids. Tell them to make sure their mic isn't, that they aren't muted. Their volume isn't muted. For liquids, let's think about it for a second. Let's say that I have 100 milliliters of water. I can take that water from a graduated cylinder and pour it into a flask, a really big flask. It's still 100 milliliters of water. So what that means for the shape and the volume, the shape of the water is variable. It depends on the container. If you look at the graduated cylinder, that's kind of tall and slender. And then the big flask, it's going to be kind of laid out because it's only 100 milliliters, so it's going to be pretty level and flat. But the volume of water is still the same. It's 100 milliliters no matter what container you put it in. So the volume is fixed. Let me know if that distinction makes sense to you. The shape of a liquid is variable, changes with the container. The volume, however, is fixed. It stays the same no matter what container it's in. I know a lot of us are still getting settled, but let me know if you're rocking with me with liquids. Okay. Yeah, this is a lot more of the me talking at you and then being like, okay, so y'all still with me? Or is it just glazed over eyes? Okay. The next property is compressibility. Just like a solid, you're not really going to compress a liquid. So that's not significant. Energy-wise, it's going to be greater than the solids. We're going to call it medium. The particles are still closely packed, but not as tight as a solid. And those particles are able to flow past each other. Hence, you have a liquid and it kind of flows when you pour water, right? So the energy associated with that, we're going to call that medium energy in between solids and gases. Gases are a little bit funky, and we're going to spend a whole chapter talking about gases at the very end of the semester. So we're just going to touch the surface today, but we're going to kind of bring back all of this information and more when we get to chapter 10. The shape and volume of a gas are both variable. If you think about blowing up a balloon, let's say you're having a birthday party and it's, post-COVID times because we're free. And you have a niece or you have a child or somebody and you're throwing a birthday party. You're blowing up balloons. You can blow up a balloon with a certain amount of volume. Take that same volume of air and try to blow up a much bigger balloon. It's going to be the same. You're not going to be able to blow it up the same way, right? Because that gas is going to expand. It's going to look very different. So the shape and the volume of the gas depends on the shape and volume of the container. It's the only one where both of them are variable. And because you can change the volume of a gas, that means that you can compress it in a significant manner. You can compress a gas to make it fit into a small volume, and then you can open that box up or that container and it will expand. In terms of energy, it's the highest. The particles are very far apart. They're zooming around really quickly, hardly interacting with each other at all. And like I said, we have a whole chapter on gases, so this is really as much as we're going to do for this chapter, chapter 3. You'll need to know all of this information and be able to talk about it and answer questions. Okay, so you don't understand the gas and compressibility. I'll give you an example. Let's say that I had a cylinder with a piston in it. Okay, that's what that is. That's a piston that you can move up and down. I can have gas in that piston, which I'm going to represent as green dots. I've got 8 green dots. That's all my gas particles. If I take that same container and I raise the piston up a little bit, I've still got the same number of green dots. But now the volume is bigger. So if I go this way, I'm expanding. I lift the piston up, the volume expands. If I go the opposite way and I push down on that piston, the volume gets smaller. That will compress the gas closer together. Good. I love it when visuals work. Sometimes you just be out here and it's like, oh, so you still don't get it? So I've been playing Pictionary by myself? Okay. Let's try again. But it's really exciting when it works. So that was the states of matter. Now we need to talk about how we can change from one state to another. So that's a physical change of state. There's terms that we use when we talk about going from a solid to a liquid, liquid to a gas, and the reverse. Most of these terms you already know. Let's say that you had a cube of ice, poured a drink, then you forgot about it, left it on the counter. You come back, you don't see any ice chunks anymore. It is a liquid. What happened to the ice? It's not a trick question, I promise. It melted. So to go from a solid to a liquid, that process is called melting. What's the opposite of melting? You're going from a liquid to a solid. What's that called? It's freezing. I told you, you already know this stuff. We're just making sure that everybody has the same framework. Now, you forgot about your drink, the ice melted, oh well, sad day. But you're back in the kitchen because you're hungry and you finna make some pasta. So, you gotta get that pot of water on and you're gonna make a gas, right? Because that's what happens when you heat the water up. What's that process called when you see all those bubbles coming up in the water? Evaporation is one word. Boiling is what I was looking for. So evaporation and boiling are related. Evaporation just happens at the surface. Boiling is when you see those big old bubbles coming from the bottom of the pot of water and rising all the way up through. That's when the whole thing is boiling. The opposite of that, going from a gas to a liquid, is called condensing. So if you have ever been in your vehicle or somebody else's vehicle and the temperature differential is crazy, it's warm on the inside, cold on the outside, you might get some condensation on that front windshield because that glass is really, really cold on the other side. So all of the water vapor that's in the air, once it hits that glass, it says, oh no, we can't do this. And you see a water droplet form. These are the terms that you'll need when we're talking about going back and forth between states of matter. Now there's two more words that we need to add here. And that's going from a gas to a solid and from a solid to a gas. These you may not be familiar with. To go from a solid to a gas directly without having a liquid form, that's the other one. So deposition is going from a gas to a solid. Sublimation is going from a solid to a gas. So the example I give in the video is talking about dry ice. Dry ice is just solid carbon dioxide. And if you have dry ice just sitting out, you'll see kind of wispy vapors coming from it. That's just carbon dioxide gas. So it skips right over the liquid phase. It goes straight from solid, super cold, to being a gas. You'll need to know all of these terms and how they relate to each other. In the lecture notes from the YouTube video that's already posted, you'll see a blank one of these slides. I encourage you to use this to test yourself and just kind of use it for your notes. It's a great way to study. I also have the completed one with pretty pictures and stuff in it too. So you've got all the options in terms of knowing these terms and examples. Are there any questions here? Okay. Moving right along. The next portion is talking about classification of matter. Since we started off talking about the states of matter, we should probably talk a little bit more about what matter is and how we can classify it. Makes sense. Matter is what makes up all the things. If it is a substance with mass, it is made of matter. But that's a really big category that everything can fall under. We need to have ways to talk about compounds and elements and mixtures a little bit better. What I'm going to give you here is the kind of how you can identify these things, not their exact definitions. For the definitions, you'll need to go to the video and the notes. Right now, I'm just going to give you some context if you haven't been able to watch the video, so we can do a little bit of practice together. For mixtures, we're talking about two or more substances that are physically combined. And you can separate them by physical means. Examples of that would be boiling and filtering. Those are two physical methods that you can use to separate a mixture. If we break down mixtures even more, we've got two classes: heterogeneous, and that's where you can clearly see the components of the mixture. The example that's given here is like oil and water. They don't really mix very well. You can see the oil sitting on top of the water. That's a mixture, and it's a heterogeneous mixture because you can clearly see with your eye the two components that comprise the mixture. Then you can have a homogeneous mixture, and that's where you can't see it. Everything, all the components are uniform throughout. And the example given for this is salt water. So you can see an IV bag hanging there. It's 0.9% sodium chloride. If you look at a glass of salt water and a glass of regular drinking water, you couldn't tell which was which. You'd have to taste it to see. All of the salt is mixed in with all of the water. You're not going to have a pocket of salt over here, a pocket of water over there, a salt crystal floating in the middle of the glass. No, it's all going to be dissolved and evenly distributed. That's mixtures. Let me know if you're still with me. Cool. Now we'll go to the right side of the flowchart. We'll talk about pure substances. Pure substances have a definite composition. So if you think about a mixture, let's say I had salt water, right? I can put 5 grams of salt plus 20 grams of water. I could put 50 grams of salt and 500 grams of water. There is no definite composition. Salt water just means that there's salt in water. I could put as much or as little as I want. With a pure substance, we're saying, no, this is defined. A pure substance means I have a certain amount of X, a certain amount of Y. With a compound, we have two or more elements, and they're combined in a ratio that always stays the same. Here shown is water. That's H2O. It is always 2 hydrogen atoms and 1 oxygen atom. If there's any more or any less, it's no longer water. That's a compound. Compounds also cannot be physically separated. If you boil water, then you just don't have water anymore. You're not breaking apart the water only using physical means. You have to chemically separate the hydrogen and the oxygen. And if you do that, you get elements. Can't break down any further than an element, at least by chemical means. And all the elements are found on the periodic table. So gold, for example, that is an element. You can't do anything to it to break it down into different components using chemical means. Is everybody clear on these different terms? Because the next slide we're going to be doing some practice. Let me know if you're ready for practice. Okay. So we need to label each of these as a compound, element, or mixture. For each of the mixtures, you have to label it also as heterogeneous or homogeneous. So let's go through and do these together. Number 1, we've got sodium metal. What do you think it is? Compound, element, or mixture? You can put C, E, or M in the chat. So sodium metal is actually an element. You'll have a periodic table for chapter 3 forward, and you'll get to know the elements. Sodium symbol is Na, and sodium just happens to be a metal. Okay. So anything that's on the periodic table is an element. What about number 2? We've got sodium chloride, which is table salt. Compound, element, or mixture? Yeah, that one's a compound. Yes. Mm-hmm. So sodium chloride is NaCl. It's two elements put together, and a compound is composed of two or more elements. Okay. Number 3, we've got salt water. And yes, we talked about this one. This one is a homogeneous mixture because you can't see the salt in there. It's a mixture for sure because you can separate the salt out. But you don't have to do anything chemical to do that. You can heat up the water and that will make the water boil off and you'll just be left with the salt. So what we're talking about here, so a mixture itself is two or more substances. So we're already in the multiples of things category. But the difference is, can you look by eye to see a clear distinction of what components are in the mixture? For a heterogeneous mixture, you can look at it and see all of the components in the mixture. So if you think about baking, okay, I'm going to give the one example because if you had a question, somebody else did too. If you're baking something and you put all of the ingredients into the bowl, right? You didn't mix them. You just have all the ingredients. You got your flour, maybe you got some eggs in there. It's, like you're making muffins or something that you can just kind of mix it all in the same bowl. Some sugar, vanilla. You can see all those individual components, right? That's like a heterogeneous mixture. You can see all the components. When you mix it up, you shouldn't see a pocket of flour here, a little egg yolk there, a splash of vanilla in the corner. It's all one thing. It looks like all one thing. And you wouldn't know that it's comprised of multiple different things without doing some kind of testing to separate them. So let me know if that helped clarify or if it made the cloud of confusion heavier. Hopefully not the latter. Good. So this fourth one, brass, is a little bit tricky. Brass contains copper and zinc metal, okay? It is a solid. Brass is a solid. So you can have brass fittings for plumbing and things of that nature, brass instruments like trumpet, trombone. So it is a solid thing. It contains copper and zinc metal. You might be inclined to call it a compound or even an element, but it's actually a homogeneous mixture. The reason is you can physically separate these two. They have different melting points. So you can heat up brass and you'll melt one metal while the other remains solid. So remember that part of the definition of being a mixture is you can physically separate it. Boiling, melting, that kind of thing. Filtration. So I always put that example on there just to kind of make sure you understand what a homogeneous mixture is. So does everyone see that distinction? This last one here is a piece of metal in water. Oh, yeah, go for it. Okay. So, the copper and zinc metal, that's what makes brass. You can heat brass and it will cause one metal to melt before the other. Now, I can't remember which one has the higher melting point, but you can separate the copper from the zinc using physical means. Because you can do that, that makes it a mixture. A mixture is something that you can physically separate. Is that clear? Okay. You're welcome. The last one is a piece of metal in water. Which one is it? Compound, element, or mixture? It's definitely a mixture. And it's a heterogeneous mixture. Because you can clearly see the metal and the water. You'll need to do these types of problems for your homework and for the next exam. Remember that Chapter 3 is on Exam 2, not Exam 1. Is everybody clear on the kind of question you'll have to answer from Chapter 3 so far? Now we're moving on to metals versus nonmetals. Most of the periodic table, it's metals. A few of them are nonmetals. We have some elements that are semi-metals. I talk about semi-metals more in the video. But semi-metals are just kind of, they're neither metal nor nonmetal. They have a combination of characteristics that pull from each list. What you'll need to know is the general characteristics of a metal versus a nonmetal. Just know that metals and nonmetals are pretty much opposites. Metals are usually solid. Nonmetals, solids, but they can also be gases, liquids. In appearance, metals are going to be shiny. Nonmetals are kind of dull. So you get the idea here. Metals are malleable and ductile, which means that you can hammer them out and you won't shatter them. You can extrude them into long wires, that kind of thing. They won't break. Can't do that with nonmetals. They're very brittle. You use a hammer, bam, it's done. So these characteristics you'll need to know. I'm not going to continue all the way through the list. I know y'all can read. Make sure that if I give you a list of characteristics, like an element has a high density and conducts heat and electricity very well, is this element most likely to be a metal, non-metal, or semi-metal? You should be able to tell me it's a metal. Let me know if that makes sense. Okay, I can repeat the last part that I said. That was kind of the example. Let's say I asked you a question and I said an element has a high density and conducts heat and electricity really well. Is that element most likely to be a metal, semi-metal, or a non-metal? You should, by knowing the characteristics of metals and nonmetals, be able to say, oh, high density, good conductor, it's probably a metal because it checks off things in the metal category. You're very welcome. Here's the periodic table. We've been talking about the elements. Here it is. I'm going to provide a periodic table for you for class for chapter 3 and forward. Periodic tables can have a lot of information on them, but they are always arranged according to increasing atomic number. In terms of where metals, semi-metals, and nonmetals are on the periodic table, you need to know that. On this periodic table, they're color-coded. On the one that I give you, they will not be. The metals are mostly on the left side of the periodic table. And again, most elements are metals. Then we've got semi-metals, which I'm going to leave those for last, and non-metals. The non-metals are in yellow, and they're on the right side. The semi-metals are in between. That's pretty much all you need to know for chapter 3 about the periodic table. Chapters 4 and 5 are really where we dig into the periodic table, the history of it, and all the information you can get just from looking at the periodic table alone. So we're not going to go into it too much in this chapter. This is just the introduction. Now, one more thing that I'm sure you know, but I want to point it out. So you'll see a 1-letter or a 2-letter symbol. That's the unique symbol assigned to each element. On the periodic table that I give you, the names of each element will be spelled out underneath their symbol. The number that is in this top left-hand corner is the atomic number. I'm not going to tell you what that is yet. Just know that it's there, and that's what it is. That's more information that you'll get in chapter 4. What you'll need to be able to do with this information is answer a question like, an element on the periodic table is located on the left side. Is it most likely to be a metal, non-metal, or semi-metal? That's the type of question that you'll need to answer. So let me know if you're still good on the periodic table. Okay. We got a couple more things to do before we get to talking about the exam and break. So keep holding on. I know this is a little bit more lecture-y than usual, but chapter 3 really isn't a lot of math. So we're going to get into a little bit more active learning here. Chemical formulas. We're going to really dive into chemical formulas kind of end of chapter 5 and like all of chapter 6. This is just the introduction. Chemical formulas, that's the language of chemistry. And in each molecule, you see the symbols for the elements, and you see these little numbers. These are called subscripts. That subscript tells you how many of an atom you have. So if I were to read this and try to figure out, okay, how many carbon atoms do I have? Then I'd look at the C. C is carbon. And the subscript says 27. So there's 27 atoms. Looking at this same molecule, cholesterol, if I tell you that hydrogen is H, how many hydrogens do I have? I have 46. The oxygen, that's O. We don't see a number there. When you don't see a number, there's no subscript, then there's just one. Now let's go up to A, because it's a little bit more involved. I want to point out that we have some parentheses here and a number on the outside of the parentheses. There's another subscript. What this means is just like it would mean in math. If I had 3 times x plus 5, you have to distribute that 3 to everything. Same way with this 3 and the COOH. I have to multiply the C times 3. I have OO times 3. I have hydrogen times 3. With that said, I want you to figure out how many carbon atoms, hydrogen atoms, and oxygen atoms there are in this compound. I'll give you 2 minutes to do it, and then we'll go over it. Alrighty. Let's start with the carbons. Everywhere you see the letter C, you need to count it. There's a C with a 3 subscript, so that means we've got 3 carbons. But that's not the only one. There's also a C in parentheses. So that means you take the 3 and multiply it by how many carbons you have in here. So we've got 6 carbon atoms. We have to do the same thing for the others. I'll do hydrogen in green. There's a hydrogen there, there, and there. We've got a 4. Plus, we see an H that doesn't have a subscript. So we'll count that as 1. Then we see 1 hydrogen in the parentheses. Just like with the carbon, you have to multiply that 1 hydrogen by 3. That's a total of 8 hydrogens. Last, we'll look at the oxygens. We've got an oxygen there. Actually, I'm going to change that to a purple because that's a little bit too close in color. Want it to stand out a bit more. So there's one oxygen. This time we've got two oxygens inside of the parentheses. So we need to take the 3 that's on the outside and multiply it by 2 for 7 oxygen atoms. So let me know how you did. Does this make sense? How we could count up all the different atoms in a molecule? Yeah, it shouldn't be that bad. You just got to pay attention. Close attention to detail. The 3 is right here on the outside of the parentheses. So it's the same 3 that we're using to multiply everything else inside the parentheses. The 1 is coming from here. When you just see the letter with no subscript, then you count it as 1. No, it applies for everything. That's just the rule. You're very welcome. We can also do the reverse. So what we were doing was writing out the composition, right? This number of carbon atoms and that number of hydrogen atoms. We can also write a chemical formula from the composition. I'll do the first one. I'll let you do the second one. Carbon is C, hydrogen is H, oxygen is O. If I'm going to write this composition as a chemical formula, I write the symbol, and as a subscript, if the number of atoms is more than 1, I write it out. For hydrogen, I have 8, so I put a subscript 8. Oxygen, I have 1 oxygen atom, so I'm just going to write an O without a subscript. I want you to try B. I'll give you a minute, and then I'll write it out. And it's a little hard to do this in the chat because you can't really do subscripts. But try it out in your notebook, and then I'll write it out. Okay. For lysine, which is an amino acid, it's part of proteins in your body. We've got 6 carbon atoms, so we represent that with a C and a subscript 6. 14 hydrogen atoms, so we have an H with a subscript of 14. Nitrogen is N, so we write N with a subscript of 2. And oxygen, we also have 2. So we write an O with a 2. Any questions on this? You'll have a periodic table, and for your homework, you can use the one that I give you, or you can use one that you find online. Either way, it'll have all the information that you need. So let me know if you're ready to move on. So the last topic we're going to cover for Chapter 3 together today, we're going to talk about properties and changes. We'll start with physical properties and physical changes. I want to go through and just give you a little bit of an idea of what these two phrases mean, and then we'll do some practice together. In general, when you're talking about a physical property, We're talking about the characteristics. So that could be appearance, oh sure, and remember this will be posted too. The notes will be posted. So if you didn't catch something, you can always just look at the PDF. No problem. So physical properties, we're talking about the characteristics of a substance. Appearance, like dull versus shiny. Color. Pliability. Melting point. Boiling point. Those are all characteristics that you can observe without altering anything about the substance. A physical change, however, we're talking about a change of state, like liquid to gas or gas to solid, or a change in shape. If you cut something, you compress a gas, that kind of thing. So let's go through these and say whether it's a physical property or physical change. We've got a good conductor of electricity. Do you think that's a property, like a characteristic, or is it a physical change? I'll give you a second because you might still be writing stuff down. I agree. That's going to be a property. In the video, I used the analogy of if you're looking for a house or an apartment, the characteristics of it, how you would describe it. How many rooms does it have? How many bathrooms does it have? You know, is the floor carpet or is there hardwood? How big is the kitchen? You know, what's the square footage of the place? These are all characteristics that you can gather by just looking around. You know, you can look underneath the carpet a little bit. You can count how many rooms there are. Oxygen is compressed. Is that a property or a change? It's a change. If we go with the same analogy of looking at a house or an apartment, a physical change would be maybe you painted a wall or you moved a piece of furniture around, something like that. What about high melting point? Property or change? It's a property. And the last one, melting ice. It's a change. Now I want you to take a second and look at these phrases. For the changes, we had something is compressed, or we had melting. Those are verbs. So a change is usually going to have some kind of action verb associated with it. When we get to chemical changes, you'll see that it's the same thing. So for a physical change, you've got a change of state or a change in shape, where something is being compressed or expanded, something's melting, something's, freezing or boiling. Those are all changes, and you can see a verb. There's some kind of ing or is something. That's one way that you can tell the difference in general between a property and a change. Does everybody see that difference? I can repeat that. So I'll repeat it. For a change, you usually see some kind of an action verb. Something's melting, freezing, boiling. Something's compressed, expanded. With the properties, they're just descriptors. Good conductor, high melting point. Nothing is happening. It's just a list of characteristics about a substance. Does that help? Great. Now you've got to do chemical properties and chemical changes. The idea of a property is still the same, it's just a chemical property. What we're talking about here is chemical potential. What that means is what kind of reactions can this substance participate in? With a chemical change, it's simply describing a chemical reaction. And I talk about evidence that you can see of a chemical reaction in the video. I'm not going to go over that. It's pretty simple. And we'll revisit it in chapter 7. The real difference here is in semantics. It's about the structure of the sentence or the phrase. So the first one, gasoline can combust with oxygen. That is talking about potential, what gasoline can do. That's a property. A burning candle, that's a change. Something is actively happening. So we were saying a burning candle, that's a chemical change. Fire, that is a chemical reaction. So let's look at the other two. A banana turns black. You think that's a property or a change? It's a change. With a chemical reaction, you're looking for color changes, heat loss. You could also have heat being absorbed. gas formation, aka bubbles. Those are all different ways that you can tell a chemical reaction is taking place, which means we're talking about a chemical change. Let's look at the last one. Reacts with strong acids and bases. Is that a property or a chemical change? It is a property. We're just going down the list of the things that something can do. So let me know if this makes sense. For the exam and for your homework for Chapter 3, you'll need to be able to label something as chemical or physical, property, or change. So any combination of those, I could say physical property or chemical property, and you choose which one it is. So let me know if that's good for you. If it's not, I want to know that too. I will post some Chapter 3 additional practice problems for you to look at when you have the brain space for Chapter 3. Right now, you might be a little bit concerned about an exam that we have coming up this week. Totally understand that. So in terms of Chapter 3, here are your reminders. 1. There is far more to Chapter 3 than what we covered today. I went over the things that I needed to tell you how you're going to be assessed of your understanding of the information and some of the concepts that I want to make sure are clear. There's more to the Chapter 3 video than what we covered, but it's not difficult. It's just vocabulary. Those topics will be included on the homework and Chapter 3, the exam 2 that will have Chapter 3 on it. So we'll do exam review just like we always do for exams. And when we get to that, I'll make sure to have some more Chapter 3 questions that are representative of some of the things that we didn't cover specifically in the live lecture, but were covered in the YouTube pre-recorded lecture. To help y'all out a little bit, I know this is your first exam. You might need to spend a little bit of extra time. So I am giving you until Sunday, February 28th, the end of that day, to complete your Chapter 3 assignments. Just know that your Chapter 4 assignments are also due on the same day. So work on Chapter 3 as soon as you can and get it out of the way. But I didn't want to force you to take your exam, and let's say you take your exam on Friday, then that means Saturday or Sunday you have to watch the lecture, take notes, do the homework, and do a quiz. I don't want to do that to you. But don't put yourself in a hole and wait until Sunday at 7 o'clock to be like, oh, I should do my homework on the 28th, because it's going to be struggle to do 2 chapters worth of work at once. Everybody good on that? We understand the expectations? All right. Now I want to take another minute, or probably more like 5 minutes, to talk about Exam 1. If you haven't noticed, there's a folder in course content. It is called Exam 1. Currently, there is no exam in it. However, it has all of your reference materials. So the equation sheet and whatever else I say you can use for that exam that I would provide. It will also have exam 1 once it's posted and available to you. It will become available tomorrow, which is Wednesday, at about 9 a.m. And it will remain available until Friday at 11:59 p.m. So you have to start your exam sometime in that window. I do not put a timer on it. However, you must complete the exam in one sitting. Other things that you can have while you're completing the exam, because remember you have to use Respondus. So Respondus is required. And all the Chem 103 courses do this, so we have to be together on this. It's uniform. You can also have a scientific calculator. Not your phone. You can also have some blank scratch paper. And a pen or a pencil. That's in addition to the equation sheet. So print the equation sheet beforehand and have it with you. If you don't have access to a printer, then you can copy it down onto a piece of paper and just let me know that's what it is. If you have a Chromebook or you're like using your phone, Respondus will not work for you. So hopefully by now you have secured an alternative way of taking your exam using Respondus. If you're close to campus, you can borrow a laptop. You can take your exam in the library or another campus computer. You can use a computer from a friend or family member that you trust who does not have the vid because you don't want to get sick. But you have to use Respondus. Any questions so far about the logistics of the exam? Does knowing how many questions really help? I'm going to answer you, and the answer is, I don't remember how many, but it's probably about 15 questions. But does knowing how many questions really help? What does that do? It's a mind thing? Okay. Yeah. I'm not here to trick you. I'm not trying to make you take a 5-hour exam. Everybody has stuff to do. Look, I'm in here lecturing. I heard my child crying, and I'm like, am I going to have to handle that? Like, we have things to do. College is a big part of what you're doing. It's a big commitment, and it's a big price tag, too. But y'all work. You got family to take care of. And we're in a whole entire panorama pandemic. So I understand y'all have stuff to do. I'm not trying to trap or trick y'all. I'm trying to help you get what you need so you can keep it moving. So my exams, if you look at the exam review and you can do well on that, then you should do well on the exam. There's no surprises. I don't slap in a concept that we never talked about. That's just not my style. What I care about is, do you understand the material? If you do, great. Here's an A. If that's everybody, then here's all the A's. I'm not trying to get a certain quota of, well, I have to have this many people fail. No. If everybody wins, then everybody wins. That's great. So hopefully that eases the tension and the anxiety surrounding that first exam. Yes, there is an answer key for the exam review. In the exam review folder, there's the reviews, and then there's a folder for answer keys. Yes, what's your question? Is there a question? Okay. So I think that's it in terms of logistics. Just make sure that when you're ready to take the exam, you open the Respondus Lockdown browser. I posted the link and the quick start guide in the course content. So if you have not already downloaded Respondus, use that link. If there's no more questions about the exam, we have a decision to make. We can take a break for a few minutes, 5 to 10 minutes, or we can keep trucking and just do exam review, which will cover some of the questions in the exam review that I posted, and there's a couple fresh ones in here. So let me know by show of hands, or you can say me. Let me know if you want to keep going. Y'all are like, all right. Then let's keep going. And when we're done, we're done. So the last class that I taught, we kept going. We ended 15 minutes early, but they were asking more questions, so we got to do some extra problems that I came up with on the fly. So if that's helpful to y'all, we can do that too. Or if we end a few minutes early and you got somewhere to be, or you just want to stop hearing my voice, you can go. So, and as always, I ain't your mama. So if you have something to do, or you're like, I'm going to do the exam review on my own, I don't need to stick around, then that's up to you. There's a question, go right ahead. No, I know you want the answer to be yes, but here's what I recommend you do, okay? If there's a couple of concepts in your brain that you're like, I keep getting this twisted around, best test taking tip I can give you. Remember exactly that piece of note that you want. And then when you started Respondus and you're in the exam, you're taking the exam, the clock is ticking, jot it down in your equation sheet or your blank piece of scratch paper. You can't bring a cheat sheet, but you can certainly recreate one. So if you practice making one and using it before the exam, you can recreate it in the exam setting, and then you still have your notes. Does that help? Yeah. I probably shouldn't be telling you that. I don't go to the instructor meetings, right? Telling you how to get the keys to the kingdom. But the truth is, in the real world, you need to know how to take information and apply it. That doesn't mean that you can memorize it, but that you can look it up and use it. And that's what I care about the most. With that said, we're going to keep trucking. We didn't cover the concept of heat versus temperature in the live lecture, but I talked about it in the Chapter 2 video. This question is from the exam review, so you can see what the answer is already. But I want to go over these two concepts of heat versus temperature to make sure we're all on the same page. Temperature we talked about. It can be, the temperature outside. It's a fairly decent day, kind of sunny out where I am. The average kinetic energy of a particle in a system. That's what the temperature reflects. So if I just picked out one particle, its energy more or less would be about this. The heat, however, is the total kinetic energy of a system. We care about each particle and how much it's wiggling around and moving. The key there is the total energy of the system versus the average. Now we can look at the question. We've got two beakers, one that has 50 milliliters of 40-degree Fahrenheit water, and another one that's got 50 milliliters of 40-degree Celsius water. We need to figure out which one contains more heat. I'm a visual person, and if you are too, for questions like this, I recommend that you write out or draw out some kind of schematic that helps you understand what the problem is asking. Now just assume that these beakers are the same size because they were supposed to be. We've got 50 milliliters in each. 40 degrees Fahrenheit for one, 40 degrees Celsius for the other. Can we just answer this straight up without doing any math? Just take a guess. Can we answer it or do we have to do some math? We can't answer it. We got to do some math. The reason is we need to know about which beaker contains more heat. And right now, we can't compare these two beakers. They've got the same volume, but Fahrenheit versus Celsius. So we can't say anything about the heat. If you have a question, go for it. I guess we'll see. If you have a question, you can go ahead and interrupt me. Otherwise, I'm going to keep on going. So I sent out an announcement yesterday, I believe, saying, hey, have that equation sheet handy. So this would be a good time to pull that up if you haven't already, or print it out if you have access, because we're going to be using some of the equations here. So I'll give you a couple of minutes to work on this problem. But the key to this problem is knowing you can't directly compare these. You've got Fahrenheit and Celsius. You have to convert one to the other. So the Fahrenheit needs to become Celsius, or the Celsius needs to become Fahrenheit. Then you can compare the temperatures of the two and see which one has more heat. There's your hint. I'll give you 2 minutes to look up the equation sheet and try to crank out your answer. You can put it into the chat when you're ready. We'll call the one on the left A and the one on the right B. So you can choose beaker A or beaker B. I'll check back in 2 minutes. Alrighty, checking back in. So when I solved this problem, I chose to take the 40 degrees Celsius and convert that to Fahrenheit. If you did it the other way, that's fine. And when you do that, you get something like 104 degrees Fahrenheit. And that makes it a lot more clear which one has more energy, heat energy. It's going to be this beaker on the right, B. you will have a question like this on the exam. So talk to me. How do we feel about this one? Mm-hmm. So parentheses help. And you may or may not be able to do that on your phone. So I would do this and use parentheses to make sure that this operation happens the way you want it to, and then you add 32 to that number. Yeah. Order of operations. Calculators are supposed to do that well. Sometimes they don't. So if there's no other objections, we'll keep moving. And yes, there's no notes on the test. Only what you can dump out from your brain onto the paper during the exam time. Here's another conceptual question, and this one is on density. I want us to work on this together because this is usually, students say it's a tough question until we talk about it, and then they're like, oh, that's really easy. So I want to make sure that we get this one because you'll see something like this on the exam. There's my sad graduated cylinder. It's got mercury in the bottom of it. And the density of mercury is 13.6 grams per milliliter. On top of that mercury is some water. Its density is 1 gram per milliliter. Also in this cylinder is a little metal piece. That's my metal. The water is less dense than the mercury, and it is sitting on top of the mercury. So that means we have an order of the least dense substance to the most dense substance. With that context, is the metal piece going to be more dense than mercury, less dense than mercury, or have the same density as the mercury? It's going to be more dense. It's sitting at the very bottom. Based on that, look at the choices. Which one of them could represent the density of the metal piece if we know it has to be more dense than mercury? I think I hear somebody's microphone still on. Yeah. This is the only one that has a density greater than the density of mercury. So when you see a problem like this, don't think that you have to go and start calculating densities. It's a conceptual question. Now, just to make sure you get it, let's say that I added another metal piece, and that piece is sitting on top of the mercury. Is that going to be more dense or less dense than mercury? It's going to be less dense. That's right. So let's look back at our choices, A, B, and C. Could A represent the density of this metal piece, the green one? No, it can't, because that would make it less dense than water. So it would be floating on top, not sitting on top of the mercury. What about B? Could that be a density of the metal? Yes, it could, because for it to represent the metal, it has to be a density greater than water, less than mercury. So it's got to be somewhere in between 1 and 13.6. So that means that C could also represent the density of that green metal piece. So everybody good on this question? You will see some variant of this question on the exam. Okay. Now we'll do a specific heat question. This one is a very straightforward calculation. Before we get to the calculations, I want to remind you of the equation and what each piece means. Specific heat, that's represented by C. You can calculate the specific heat of a substance if you have Q, which is the amount of heat that you put in, M, which is the mass, and it has to be in grams. The heat, by the way, needs to be in joules. And then we have delta T. That's the change in temperature and it has to be in degrees Celsius. And again, C is specific heat. And its units are joules per gram degree Celsius. You will get this equation on the equation sheet. You will not get the breakdown of what each variable means. That information you need to bring to the table yourself. Now let's read the question. You've got a 12.6 gram metal sample with an initial temperature of 25 degrees Celsius, heated to 32 degrees Celsius. The amount of heat gained is 125 joules. You have to calculate the specific heat of the metal. The best thing to do for these problems is identify what you have. If you are comfortable, go ahead and just do the problem on your own. We can meet up at the end. But if this is still a little bit of a question mark for you, stick with me. We've got several numbers here. First one we encounter is 12.6 gram metal sample. It's in grams, so that must be a mass. Next, we encounter 2 temperatures. That's got to be what we use to calculate delta T. Delta T, that's the change in temperature. That's the final temperature minus the initial temperature. The final temperature was 32 degrees Celsius. The initial temperature was 25 degrees Celsius. So that's our change in temperature. The last bit of information that we have is 125 joules. Since the units are joules, that means it's some kind of energy. It has to be our heat, which is Q. If you assign each of these, then it becomes more clear which variable you have to solve for. We're told in the question, specific heat. But if that doesn't mean anything to you and you're like, wait, which one is that? Hopefully you can fill in some of the other variables and then you'll be able to solve the problem. We're solving specific heat. So we're going to just fill in all of the numbers in the equation. Q is 125 joules. Make sure that you're paying attention to the units, because I could give you heat in kilojoules or something like that, and you have to convert to joules. We take that heat and divide it by the product of the mass, which is 12.6 grams, and the temperature change. I'll let you go ahead and put that in your calculator and let me know what you get. Yes, and we're answering with the right number of sig figs. You'll know how happy you're making me. 1.42. You get like 1.41 something something something. But we only can have 3 sig figs, because if you look at the problem, the temperatures, they all have 3 sig figs. The mass, the energy, all 3 sig figs. But don't forget your units. None of these units cancel out. So it's joules per gram degree Celsius. So let's say this was a problem on the exam and you had to write in your answer. There was a short answer question. What I want you to do is, if you want the chance for partial credit, remember, I grade everything. If it's a multiple choice about like how many sig figs, I can't really give you partial credit. It's right or wrong. But on a question like this, if you show me, okay, they assigned their variables, they put this equation together, but maybe you put the wrong number of sig figs, or you typed it in your calculator wrong, you can still get some partial credit. So for exams, type out your work for partial credit. Can't guarantee that your work will get you credit, but if you have the wrong answer but you have the right approach, you'll still get some points. Everybody get that part? So it's up to you. If you don't type out your work, then I can't help you out. It's right or it's wrong. But the more you can show me about your process for those short answer questions, the more I can help you out by rewarding you for showing me what you know. All right. It seemed like a few of y'all got the answer. Unless there are questions, we're going to keep moving forward. So are we ready to move forward? So this question is a throwback to the Chapter 2 check-in. There were a lot of folks who made a similar mistake in terms of writing the unit equation a little bit wrong, and then you got the wrong answer. So I want to walk through this one and kind of point out where people made mistakes that I remember, just to help you out. Also, don't just see your grade, but look at the comments that I wrote. Even if you got a good grade, if you didn't get 10 out of 10, that means I took points off for something. So it could have been for significant figures, it could have been for units, something like that. But make sure that you look at the feedback for the chapter check-in grades. I want to help you out and give you feedback on how you're doing and how you can improve. So we've got how many picometers are in 2.55 times 10 to the 8th kilometers? You're always welcome to work ahead. If you don't feel comfortable or you just want to see how I do it, then watch and participate. I start with rewriting the question. I'm given 2.55 times 10 to the 8th kilometers. I need to know how many picometers that is. When you rewrite the question, if you have a prefix on both sides, then you can't just jump from one to the other. You have to go through your basic unit that's in common on both sides, which in this case is meters. Our first unit equation will get us from kilometers to meters. The second one will get us from meters to picometers. Stop me at any point if this doesn't make sense. For our first unit equation, we have to relate these two. If you have your equation sheet, you should be able to look at the metric prefixes and fill in this unit equation. If I have 1 kilometer, how many meters do I have? You can put it in the chat. Exactly. I've got 1,000 meters. Let's write the second unit equation. You can also write it in scientific notation, and that's perfectly fine too. The second unit equation, we've got picometers and meters. What is my unit equation? If you're stuck, or this is a point where you're like, you lost me, let me know. Yeah, so there's one. We've got 1 meter is equal to 1 times 10 to the 12th picometers. Notice how, since we're relating it in meters, 1 whole meter, then we have a positive power of 10. If you think about it in terms of pizzas and slices, a meter is much bigger than a picometer. So the meter is going to be like the pizza. If I have a whole pizza, then I've got 8 slices if that Domino's employee wants to keep their job. If I've got 1 meter and I break it up into picometers, I've got a lot of picometers. It's going to be 1 times 10 to the positive 12 to make up that 1 whole meter. The other way that you can do this is to write, if I have 1 picometer, and then you fill in from the chart 1 times 10 to the minus 12 meters. So there's 2 different unit equations, but they both say the same relationship. And I saw on the homework where it was kind of like you're merging the 2, and you're saying 1 meter is equal to 1 times 10 to the minus 12 picometers. So if you do it this way, the second way, where you replace the prefix with the number from the chart, then it will always be exactly what the chart says. So if the chart says 1 times 10 to the minus 12, you put 1 times 10 to the minus 12. However, if you do it in terms of the base unit, or the basic unit, I have 1 meter, then you have to do a little bit more thinking. If it's something that is bigger than your basic unit, say a kilometer, well, 1 meter is smaller than that. So it would be a negative power of 10. If you're going from a basic unit to a smaller prefix, it's going to be positive. I talk about doing that way in the video, the big to small, because it makes sense for some people. But for others, it makes sense to just try to fill it in using the chart. Whichever way you're comfortable with, that's the way that you do, and you'll get the right answer either way. You're very welcome. We've got our unit equations. Time to write unit factors. Those are the unit factors for that one. And I'm going to stick with this second unit equation. So we're starting with kilometers. We need to get to picometers. Are picometers bigger or smaller than kilometers? Smaller. Much smaller. So do you expect our answer to be bigger or smaller than the number of kilometers that we have? I see a question here, so let me answer that first. You can use that on the test. So I put that as part of the equation sheet. It's 2 pages, so you can print it out front and back if you want, or just as 2 separate pages. All the equations, like the temperatures and specific heat and that kind of thing, and then also the chart. So I do not require you to memorize the prefixes. But we would expect, since picometers are much smaller than kilometers, that our answer should be really big. It should be bigger than something that's 10 to the 8th. Let's fill in the unit factors and figure it out, what the exact answer is. We're going to use that second unit factor for the first one. And then from our second unit equation, we need to cancel out meters and end up with picometers. So that's how we fill it in. If you're doing it this way, on your calculator, what you want to put in is 2.55 times 10 to the 8th, which you may want to use parentheses just to make sure nothing funky happens, times 1,000, divided by, use your parentheses again, 1 times 10 to the minus 12 picometers. You can call them conversion factors, unit factors. Okay. Which one makes sense to you? Because these are 2 different unit equations to say the same thing. Then don't worry about it. As long as you know how to do this way, then you're good. Some people think about it with the top way, and so I address both. But whichever one you like better, that's the one you use. So when you put that into your calculator, you should get a very big answer. When you're answering this question, don't forget your units. We're supposed to be figuring out how many picometers, so it should be some number of picometers. Let me know if there are still questions on this. If you're ready to move on, we can move on. So it shouldn't matter, but if you put it into your calculator the wrong way, then that's what matters. Not the scientific notation or not, but how you put it into the calculator. And that's something that I can help you with specifically for your calculator if you set up like an appointment or something, or you send me a picture of your calculator with what you put in, because then I can tell you, oh, you put this in wrong, or you need parentheses here. Does that make sense? Yeah, so if you want to do that, you can certainly do that. You can send it in a private message if you want to hang out for a minute or two after class, or you can just send me a course message and I can help you out. You're welcome. Oh, you were wondering where baby Hefner was? Yeah. He was asleep, and then he said, oh, no, she can't finish class without me. I'm going to be a YouTube star. So I have another one of these conversion questions, but here's my question for you all. Do you want to do another one of these, or do you want to move on to other problem types? So let me know in the chat what you want to do. I'll give you the answers to both. So when I upload it, you'll have it. So even if we don't do this question, you'll still get I'll solve it for you. Okay. I figured my other class wanted to do more examples of this too. So whatever we get through is what we get through. We may not get to all the questions, but I want you to at least have a shot. This time we're converting centigrams we're taking kilograms and converting to centigrams. You see that prefix on both sides of your question. So you have to use two unit equations. This time we're doing grams. So you convert kilograms to grams, and then grams to centigrams. I'll give you a couple of minutes to get started, and maybe since we did that other problem, you might be able to get a little bit further with this one. So see how far you can get in 3 minutes, and then I'll check in and start solving the problem. If you're still working, keep working. I'll just work with you. The first relationship we have to establish is kilograms and grams. If I have 1 kilogram, I can look up that K for kilo, and it means 1,000. So I have 1,000 grams. These are my unit factors. For the second equation, we're trying to figure out grams and centigrams. So again, if you start with one of the one that has a prefix, so 1 centigram, then you can equate that to, and look it up on the chart, what the lowercase c means. And that's centi, which is 0.01 grams. You can also write that as 1 times 10 to the minus 2. Just like you can write 1 times 10 to the third for 1,000. A centigram is smaller than 1 gram, if that's what you're asking. Okay, then yeah. Those are the unit factors. For our plan, we said we had to go from kilograms to grams, grams to centigrams. To get from kilograms to grams, we need the unit factor with kilograms in the denominator. That way it'll cancel out. To go from grams to centigrams, we need to put grams in the denominator and centigrams in the top. Our units cancel just like we expect them to. So you can go ahead and put it into your calculator. 9.25 times 1,000 divided by 0.01. You should get a big number. If your calculator gave it to you in scientific notation, that would be the answer. I didn't specify scientific notation here, so if this were an exam, either answer would be fine. But let me know how you did with that one. Did it feel a little bit better? Good. So we have this question, a rounding question, and a sample extra credit question. We'll only have time to do probably one of these, so either the addition with sig figs or the rounding, and then the sample extra credit. So let me know if you want to do adding or rounding with the placeholder zeros, and we'll do one of those two problems. So adding with sig figs or rounding with placeholder zeros. Y'all are all on the same page. So I'll still have the answer to this in the notes. I just won't go over it in the video. So we'll do this one. We have a measurement, 189,645 meters. We need two significant figures, and it has to be written in scientific notation. If we need two significant figures, which digit is going to be my last retained digit? You can tell me in the chat. It's going to be the one that we're looking to round up or down. So we're going to keep the 8 and look at the 9 for rounding. 9 is definitely 5 or greater, so we need to round up. But 19 looks really different from 189,000. We need to add some placeholder zeros. If you line up your number like I just did underneath, then you'll have a much better time with figuring out, oh, I should probably add some zeros here. Because we had to add a few placeholder zeros just to get to the right number. So does everybody see how we got to 190,000 to round? Now we have to take this and write it in scientific notation. We need a coefficient that is at least 1 less than 10. So you write out your significant figures. We've got 2 of them. And you make your coefficient. For your power of 10, you have to say, okay, I put my decimal point here. How many spaces did I have to move the decimal to get it there? And that's 1, 2, 3, 4, 5. Now it's positive in this case because the number we're dealing with is 1 or greater. It's 5 because I'll rewrite it. We have 190,000. There's an implied decimal point at the end of this number. What we did to write in scientific notation was move the decimal point to between the 1 and the 9. We have to count how many spaces are between where the decimal point was and where we put it. So that's 1, 2, 3, 4, 5 spaces. Does that make more sense now? It's all good. Okay. So let's try to get to this problem. This is a sample extra credit question for this exam. This is a question you have not seen before, and it looks like concepts that we may not have done before, but I promise you they are. We'll go through it. I'll identify those concepts, and you will see this on the exam. But it is extra credit. You don't have to do it. If you want to, go for the gold. Chick-fil-A sauce contains 7 grams of carbohydrates per serving. If a serving of sauce contains 140 calories, what percentage of calories comes from carbohydrates? Report your answer with 2 significant figures. 1 carbohydrate is equal to 9 calories. So it looks like something that we've never done before. But in all actuality, we've done both of these things. The question is, what is the percentage of calories from carbohydrates? To figure that out, we've got to do 2 things. 1, take the grams of carbs and convert that to calories. Then we have to calculate the percentage of calories from carbohydrates. This top one is simply a conversion. And you have a unit equation for that. The second part is calculating a percentage, and we talked about percentages. So conversions and percentages are things that we have definitely done. Part 1. 1 gram of carbs is equal to 9 calories. I can write 2 unit factors. And then I can use one of these to convert my grams of carbs to calories. Since we're trying to get rid of grams of carbs, we need to have it in the bottom. Now we have calories, and we can move on to the next part. So does that make sense? It's using calories and grams, but it's still just a conversion. So is everybody with me? For the second part, it's just calculating a percentage. We know that a percentage is a part over a whole times 100%. The part is what we just calculated. That's the number of calories from the carbohydrates. The whole is in the problem. 140 calories. And then you multiply by 100%. When you do that, you should get 45%. So you'll see a question like this as extra credit. There's some other extra credit as well, but it's more straightforward than this question. Are there questions about this? So that's all I have for you. If you have questions, you can hang around and ask them. If you don't, you're free to go. If you need time outside of, because office hours already happened today, then please make sure that you send me a course message as soon as possible so that you can get the time you need. The exam will be available starting tomorrow morning. You have until the end of Friday to start it. As always, reach out with course messages and I'll get back to you ASAP. I know that we have an exam coming up, so I'm going to be checking it pretty regularly.